My name is Campbell Mutert, and this is my video for Lab 3. The purpose of Part 1 was to observe the motion data of a star and the net forces acting on it to determine the mass of a black hole, which was 9.87 times 10 to the 33. The purpose of Part 2 was to determine the initial velocity required to escape a planet orbiting a black hole with the mass from Part 1 and fly around it without crashing into the planet or being sucked into the black hole. And through trial and error, I found that to be negative 3.37 times 10 to the 7th, 2.27 10 to the 6th, 0. Some of the key concepts covered include rearranging Newton's second law into the momentum update formula, the velocity update formula, and the position update formula. When there is an unbalanced system and Fnet is not equal to 0, it can be decomposed into the parallel and perpendicular components. Fnet parallel changes the magnitude of the momentum in the direction p hat, speeding up if it's parallel or slowing down if it's antiparallel. It's equal to the change in momentum's magnitude over the change in time in the p hat direction. Fnet perpendicular changes the direction of momentum, with n hat always pointing towards the center of the turning circle as shown here. It's equal to the magnitude of momentum times the change in direction over time, which is equal to mass times the magnitude of the velocity squared over the radius in the n hat direction. Universal gravitation is g times the mass of 2 times mass of 1 over the magnitude of r squared times negative r hat. R in this equation is how far m2 is away from the source, m1, so r hat points from the source to the system. But since gravity is an attractive force, the direction of the force is negative r hat. Since the interactions occur in space, we assume that there are no other external forces, and Fnet is equal to the gravitational forces present, so we can solve for m2 as Fnet times the magnitude of r squared over g times m1, where g is the gravitational constant, 6.7 times 10 to the negative 11th. For Part 1, the system was the star, the surroundings were the black hole, and the initial conditions were given in the instructions that the mass of the star is 2 times 10 to the 30th, delta t equals 1 day, which is 86,400 seconds, and the initial time is 0. Input the initial conditions. The code used my email to generate the velocity components. I used these to define the initial and final velocity and multiplied them by the star's mass to calculate the initial and final momentum. Then I determined the changes in both from initial to final as delta v and delta p. dp dt was the change in momentum over the change in time, which was equal to Fnet. P hat was determined by dividing the momentum vector components by its magnitude. d mag p dt was calculated as the magnitude of the final momentum minus the magnitude of the initial momentum over the change in time. The parallel component was calculated by multiplying that by p hat, and it was set equal to Fnet parallel. dp dt perpendicular is equal to dp dt minus the dp dt parallel, which is also Fnet perp. The mass of the black hole was calculated using the equation from m2 earlier, and the value was printed for each loop. The trails and arrows were updated to observe the components, and the time was updated. At the end of the observation period, Fnet and its components were printed along with the final mass of the black hole. So here is the model for Part 1. The final Fnet and its components are shown here. The mass of the black hole was calculated as the average from the masses printed during every loop, so over the entire orbit. It was determined to be 9.82101 times 10 to the 33 kilograms. For Part 2, the system was the ship, which is magenta. The surroundings were the black hole and the planet, which are the black and blue spheres here. The only initial condition was the mass of the black hole from Part 1. This code set up the graph and gave the initial position and radius for each object. Then I input the mass of the black hole and left the constants as is. I ran the simulation for 10 minutes because the ship was well out of the orbit there. Initial speed for both the planet and the ship were calculated as the square root of g times the mass of the black hole over the magnitude of the distance from the black hole to the object. For the planet, that was the velocity in the y direction. For the ship, I used trial and error to determine the x and y components, which were used in the velocity vector. For the 10-minute loop, the net force on the planet and the net force on the ship were calculated at each time step by summing the gravitational force from the black hole and the other object. The relative position vectors were calculated, and then the gravitational force was g m1 m2 over r cubed times r. The planet and the ship were updated using the calculated force and the velocity and position update formulas. If the ship got too close to the black hole or to the planet, a message would indicate that and the loop would break. If not, then the time would update. At the end of the time period, the Fnet on the ship's vector and magnitude were printed, along with the time and distance of the ship. So here is the resulting model and the initial velocity components that were successful. The net force is the sum of all external forces acting on the system. The rate of change of momentum comes from the change in velocity of an object with known mass over time. Both can be decomposed into parallel and perpendicular components, with the parallel describing speed and the perpendicular describing direction. For Fnet, the direction of the components can be observed, but to know their magnitude, you'd have to know all of the external forces. But for the rate of change of momentum, you can calculate it as long as you know the mass and velocities throughout time. To get the ship to orbit the black hole, I used the same code from part 2 and updated the initial velocity vector to have an x component of negative 8 to the 11 times 10 to the 5th and y component of 8.2 times 10 to the 6th. Compared to the initial velocity to escape, the x component is much smaller and the y component is larger. Sources of error include me approximating the mass of the black hole over one day. To get closer to the true mean, the model could run for longer. Additionally, the models all assume that the only force in space is gravity and there are no external forces. And the initial velocity was found through trial and error, so there could be other velocities that get closer to the black hole.